Hello, everybody out there. Today, I'm Dr. Pickle, and today I have on here as well Science Mom and Math Dad.
Hello.
Welcome.
So, one of the things that I really believe in is that the best way to teach the scientific method is not to get your hands dirty. I guess that's good too, to get your hands dirty in real nature. But another way to teach the scientific method is to come up with simple little mathematical universes that you get to explore like a scientist. And right now we're going to explore two-scoop ice cream. You have to figure out how this ice cream parlor works. Here we have the first question is, what is this? You can choose to either look at the structure of the ice cream, or you can look at its cost. Okay, so those are your two things that you can look at: the structure or the cost. So right now you can write up in the you can say that you want to explore the cost or the structure. So go ahead, say one or the other in the live stream, and we will follow suit.
So I'm guessing these are some berry flavored ice creams, maybe like strawberry on the bottom.
Yeah.
On the top.
Yeah, I think so.
That sounds good to me.
That's what the color is? Okay, and then are these individual scoops we're seeing? Or?
Yeah, let's make them individual scoops for the moment. You guys don't see anything else. And I don't know if you're seeing any live stream. I'm not.
Also, no live comments yet.
Okay, so I'm just going to go onto the Math Pickle channel here, see if we've made a mistake and that we should be following this on Math Pickle. Let's see. Are there any live comments here for us? And I'm not seeing any live comments here either.
I'm curious to explore cost. That sounds interesting.
Okay.
Well, we don't want to do it before anybody's there watching, though. I don't know. But yeah, hopefully they will chime in the chat.
Yeah, okay. So cost it is. So I am going to show you the cost for this first one here. It is a, this first, let's see. Okay, let's.
Math Dad, if you had to say,
oh my goodness, come on.
What would it be?
Oh boy, my
favorite type of ice cream.
Favorite type of ice cream.
There we go. Finally, we have the answer. That is the number 2, and that is the structure. You get a bonus. You get to see the structure of the ice cream, and you get to see the number here. Okay. You can also ask for a weaker clue if you feel a little bit confident but not super confident. Then I can give you a mini little clue about the cost of it. Okay, so that's the first one. You probably don't.
So it actually froze up a little bit. Kind of surprised. I don't know whether you can hear us. So the number 2 there, it was the cost, $2 or whatever.
Event there.
Uh-oh.
So go ahead. What would you like to do?
So just so we're clear, the number 2 there, was that the cost?
That's the cost.
You said we also got some information on the structure, and if there's a hidden,
that is also the structure. The structure for the first one is a circle. That's it.
Oh, okay. So because nothing changed. I got you.
Nothing changed. Yeah.
So my hypothesis is that all of our ice cream is going to be $2 a scoop, because that would be pretty simple and easy. That's
of course. Of course. So yeah, that would be a $2 a scoop. All of them. Okay, got it.
I don't know. The different color ice cream can't cost the same.
Well,
I bought a lot of ice cream in my day. That's plausible. $2.
If it's huckleberry ice cream made with real huckleberries, it would be more than $2, because huckleberries only grow wild and they're hard to get. So I could see there being exceptions, but that's my original hypothesis. $2
Okay.
for all the flavors.
And you think they're all circles or they're spheres?
Yeah.
Okay.
Okay. So next one, what do you want? Do you want to look at the structure? Do you want to find out another bit of information about the cost? What do you want?
I want more cost.
Cost. Okay. So for cost, I'm going to. Oh no, you don't see that. Stop that.
Well, I think we got a hint about structure for this next one.
Yeah, you got a hint of the structure. Oh, what? Go away. Yeah, I'm dealing with the 2009 old computer here, so a little bit slow on the go here. Okay, here we go. And oh my goodness, there we go. So I'm just going to give you the whole thing because it is slow. So yeah, there you get the structure and the cost. So that is the whole shebang there. I
Okay.
can give you more information if you want.
All right, so that
I'm going to give you more information to start. There we go. There, that's the second 2-scoop ice cream. What do you think about the third?
That one looks like 3 scoops to me.
Yeah, it does. It does.
Yeah.
like a water molecule.
It does.
Yeah.
So this one would cost $6 in total?
Or $8.
Nope, that one's costing $4. That one's costing $4.
That one costs $4.
Oh,
because
but
it's
there
larger.
are some secret 2s hidden there too. So okay.
Interesting.
I bet there's something sneaky going on. But okay, clearly we are getting one big one and lots of smaller ones. So that we went from 0 to 2. The next one, the structure, is definitely going to be one big one and 4 small ones.
That's your
Okay, let's see. So you're deciding not to poke. You are making a prediction. Okay, so let's see how that prediction works. And that did not work out so well for you. You do have a different structure there.
I'm going to guess the cost is 8. Because if we went 2 and then 4 and then 8, there's a pattern. That's my guess. I'm abandoning my... Ooh, and I was right.
Ba-dum-bum-bum. Science Mom is doing very well here. So we have a pattern here. So do we want to say the pattern?
I'm guessing 16 for our.
Well, that's the cost. So
Okay.
what's going on with the pattern, though? Our hypothesis then is we've got geometric growth. It's just doubling each time as you go left to right.
Yep.
Geometric growth. Yeah. So that's like 2, 4, 8, 16. Yeah. Okay. So let's see. So actually, we can rule out hypothesis number 1 now. So
That's right.
That's for sure.
Abandon that hypothesis.
Okay. So the hypothesis here is 16. And let's see how it works.
Oh, but the shape.
You are correct. You have it correct. So down here is the next one.
But the way it was growing, I thought we would maybe, I don't know why we grew more tentacles on the left and right, or it's branching off in both directions now.
Yeah.
So something sneaky.
Something sneaky.
Yeah. All right. So as we go from top to bottom, we don't actually have any information, but I think it's going to just stay the same along each column. The numbers aren't going to change. It's only as you go to the right and get more circles. So,
Okay.
Is this all part of one pattern, or are there's going to be a different pattern each row?
There will be the same pattern for this whole puzzle. So, okay, I'll give you a hint. This is just one big line. Okay. Yeah, for the slideshow, I had to put it in 4 lines, and it goes on forever.
So it kind of wraps around. So.
Yeah. So okay. This is not a 4x4 grid. Think of this as a line. So right after 16 comes this one.
32.
32.
That's called it.
Science Mom, you agree? Okay, here we
agree.
go. And so maybe you want to reconsider now that you see the pattern. Is that possible that you want to reconsider?
Wait a minute.
All right, I'm going to say 8.
I would also guess 8 based off of the scoop size.
And the picture.
If we're thinking of the actual scoops.
Okay, so 8, and the answer is 20.
What? Interesting.
Oh, and I made a mistake here. That is not supposed to be 4.
Do you have an idea?
I do have some ideas, but let me go a different route.
Okay, we are back on track now.
Okay, the next one. So, it's going to be, well,
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. The ice cream is about to be served.
24. It's
24.
going up.
That sounds
24? Okay.
good to me too.
Yep.
Okay, here we go. So there's the structure.
Okay. So now that I see that.
Okay, and the smaller part of that structure looks a lot like the one for number 8. So I think we've got kind of a fractal-like pattern going on. I think our pattern has something to do with fractals, maybe? That's a hypothesis I'm forming.
Okay.
Oh,
I don't know.
So, I mean, I'm definitely seeing some multiplication trends going on here. But
yeah, our guess.
How do we predict the cost? I was going to say 24 just because it's...
Yeah, let's say 24.
24 it is.
Yep.
Oh, we were wrong.
And again, yeah.
Time to revise our hypothesis.
Mm-hmm.
So,
but 4 times 8 is 32.
That's right. And if you look below the 4...
2 times 2 is 4.
2 is 4.
And 2 times 4 is 8.
And if you look down below that 4 again, there's another 2. There's 2.
So I think whatever is in the first circle moves over to the second and is doubled. No, that doesn't work for the 20. Yeah. I'm not sure.
So
we're going to poke again, or?
Yeah, let's poke again.
Poke again. Here we go. You want to poke for structure or for, I can tell you a number that it's less. That would also be another option.
I do want to see the number. So
you want to see the number for sure? Okay, the accurate number. Okay, so I will tell you right now that this number here
40.
Is 40.
You were right.
Okay. So if that number is 40, so what I'm noticing is that we have 4 times, well,
your fingers
lots of even numbers. All right. Block out. I don't know. Lots of multiples of 8 in there, and multiples of 4. Yeah, I don't know. Okay.
Are we getting kids in the real audience here?
I'm not seeing any live chat on our end. So
okay, I am seeing some live chat here.
Oh, good.
Good.
Yeah, but people say it keeps freezing. So that's appropriate for an ice cream 2-scoop ice cream puzzle that it freezes. So, yeah.
So this looks to me a lot like factor trees. So I'm seeing that, yeah, each circle gets broken up into factors. So I think that's what we're seeing here. But the problem is the number 40 can definitely break up in different ways into factors. So, I mean, it could be 4 times 10, or it could be 8 times 5. And I don't have any idea what the rule would be for breaking it up. But my guess is you always pick... I'm
going to put down this math dad. I'm going to put down factoring trees or prime factorization trees. Yeah. So I'm putting down that as an idea. Oh, and we can rule out hypothesis 1 and hypothesis 2 now.
That's right. Those are both proven false.
Yes.
I would love to see the structure for 40.
So 4, 10, and then you'll break those up according to factorization. That's what I'm going to guess. It'll be a 4 and a 10 as the... Oh, or maybe not. Maybe it'll be a 5 and 8. Mm-hmm.
Or a 2 and 20. Find out. There's our 40.
Okay. Do you want more, or do you?
Yes, with more.
So I think it'll be 5 and then 8 if when you reveal them. That's my guess, but
yes, and that is going to work. Yeah.
But yeah, how would we have predicted that it would be 5 and then 8 instead of 8 and then 5?
The smallest
or
one goes on the other side. I don't know.
So yeah, maybe are they in increasing order from left to right? I'm looking at the second level dots, 5 and then 8. Ooh, I think that pattern actually holds everywhere, so that at least
Okay.
at each level of factoring, you're going to do smaller factors first and then larger factors next.
But then how are you going, how are we choosing the numbers? That's the real mystery that I'm curious to learn.
Yeah, why not 4, 10 instead of 5, 8? And also, why did we skip 36? I've got to say, your ice cream is getting pretty expensive here.
It all comes down to the ingredients. Yeah.
All right, what's your
pay for premium product?
I think the next one's going to be 48. So
48. Okay. So do you want to find out the whole thing? Would you like to see the structure?
Let's see the cost.
Yeah, we need just the cost. Let's poke the cost.
You want the cost. Okay. The cost is here.
Uh-oh.
That's just 6? Nothing else? Oh, 64. Okay.
64. That is not 48.
No, it is not. And then how would we break up 64? Because we could do 2 times 32, or 4 times 16, or 8 times 8. We've got options here. Okay, so when we look at the earlier rows, I see that as close as possible, those seem kind of balanced. So I think you want to take the 2 factors that are closest to each other that multiply to be 64. So in this case, 8 and 8.
So it's reasonable to me.
So instead of like 2 and 32, I would do 8 and 8.
Okay, let's see the structure and see if we're right. Oh ho! Good job, Math Dad.
Oh.
So yes. So do we want to say that hypothesis? Let's make these hypotheses. Let's make those. Let's just remove them because they are not working. And hypothesis 5.
Is that at each branch we choose the 2 factors that are closest to each other.
That sounds
but that multiply to be the number above.
Closest.
I like that. I'm still totally stumped about how to predict our next number, though.
Yeah, I don't see the pattern there either. He's got something sneaky going on.
So I'm going to say for sure it's larger than 64. It's going to be increasing.
We are seeing an upward trend here, and there are a lot of 2s that are factors there. So, I mean,
I'm going to guess 80. 80 is my guess.
80.
What's your guess?
So that has. Okay, 80 sounds plausible. Let's go with 80.
Okay. And you just want to see the number first?
Just the number, yeah. Because
okay, there we go.
The rest of our prediction will all be based off of whether we got the number right.
Oh, 72. That is not 80.
What? What?
Huh.
Well, 72 we know has a lot of factors. But okay, so if we were to follow our previous hypothesis, we'd be looking for 2 numbers that multiply to be 72 that are as close together as possible. So that would be 8 and 9. And then our other hypothesis was that we should put them in that order, 8 on the left and 9 on the right.
And then factor them down from there. So then you'd have, the 2, the 4, 2 and the 4, and 3 and 3. Nice.
I think that just verifies so that we've kind of got the placement of things figured out, or at least a hypothesis that has not yet been contradicted.
But we still don't know how to predict the next number.
No.
Like, I'm not sure how we got from 64 to 72.
Right. Yeah. Why did we?
Unless, what if because you have 8 and 8 for 64, and what if you just increase the second number and then you have 8 and 9? Does that hold if we look back? Because 4 and 8, and then you have 5 and 8. 4 and 4, and then you have 4 and 5. So if our next numbers...
Yeah, but earlier, I mean, why did we go from 2 and 2 and didn't go to 2 and 3? Like,
I don't know.
Yeah.
That falls apart there. I don't know.
So.
But just for fun, if that were correct, then our next one should be... Never mind. It totally falls apart.
Yeah, I have no idea.
You know what?
My hypothesis there falls apart.
Your poking goes awry. You make a false step in the next experiment, and you end up with the structure, but no number.
Ooh.
Okay.
This is interesting.
Well, I see a solitary circle on the right. I think that has to be a prime number.
I think you're right.
And the number on the left, every time we've seen an 8, then we've gotten that same factor structure. So there's a chance that the one on the left is an 8.
So I think it's a 88. 11 times 8. That's my guess.
All right, that's a good guess.
Oh, I was right.
Now, why was it not 8 times 10? Why are we skipping?
I don't know. I don't know. I'm very curious, though. This is fun. All right, what's your prediction for the next one, Math Dad?
Go for 96. But do I have a good reason as to why? No, I do not have a good reason as to why. I'm seeing we like lots of factors of, or powers of 2. So if we can get a 16 in there, that could be cool. Whoa, that's a lot of factors. So now, so on the left, if we saw something like 8 in the, so go down one level, that could be an 8, and the one on the right could be a 16. 8 times 16 is 128. That's quite the big jump. Now,
Oh, and you were right. All right, give us a little hint, Dr. Pickle. How did we go from 88 to 128? I am very intrigued.
So if anyone out there in the wider audience has any idea, so Math Dad and Science Mom have definitely figured out once they see the number or once they see the structure, they know what's going on, but they're having a difficult time in figuring out what is that next structure?
Yes.
What is that next number? Yeah.
Well, and
I'll give you the next structure.
It's the same thing. All right. No, it's not the same thing. Well, let me just point something out on the previous one. I mean, how do we know that it wasn't, I don't know, 3 to the 7th power instead of 2 to the 7th power? Because we would have ended up with the same type of factoring structure. So, I mean, Dr. Pickle likes his 2s a lot, and I don't know why. And we got to, maybe it gives us smaller numbers.
And I will tell you that if this was 3 to the power 1, 2, 3, 4, 5, 6, 7, it would have the exact same structure. You're right.
So we're not always going to get down to 2 at the bottom?
Well, there's no reason we had to, but there's got to be some method to the madness of where these numbers are coming from.
All right, so what's your prediction for the next number, Beth Dad?
Well, we are increasing, but how much are we increasing? I don't know. It'd be 144. So we're getting numbers with lots of factors.
Okay, and does 144 work here? So 144, you would split it how, according to your hypothesis that you split it as evenly as possible?
That's right.
And then you'd have to have identical trees on each side if you did 12.
That's right. So we know it's not 144. I'm not saying this is easy to figure out, but it's not. It can't be 144 because you would expect it to split 12 times 12.
That's right. And I was trying to go for the 9 times 16.
So
and that's
maybe
not going to work.
Would 140 work? Because then you could have 10 and 14.
10 and 14. So the 14 would go on the right. The 10 would go on the left, and we don't have quite enough factors.
And 5 we don't.
So okay. So the bottom right branch seems to be like a 16 would be. So I can imagine that a 16 would work on the bottom right,
and a 10 would work on the right because then you'd have 2 and 5
left.
on
so
the
you think
left,
it's 10 and 16, so there's a 160.
Yes. Ooh. Go Math Dad and Science Mom.
Yep.
It took us a little while, but we got there.
Yeah. So we've only got a few more. So I'm not going to tell you the last hint because that's the last thing that you need. That's the last thing that you need. How are we coming up with these numbers? Because everything else you guys understand. Like everything else, if we go on to this next one here and I show you this one, you're going to say, okay, what would that be? And you're probably going to get there pretty fast.
Yeah, probably 11 times 16, so 176 would be the...
That's right. That's right. Okay, so you're having no problems once you see the pattern or once you see what the number is. But the most difficult part of this universe is what the heck is the next ice cream scoop here? These crazy ice cream scoop. What the heck is the next one? what does the pattern look like?
Okay, so I would go start speculating that we want powers of 2, but that once you have it, you increase one of the numbers. But no, that's...
I have to say, I'm very pleasantly stumped. I am totally
Good.
no idea, and it's really kind of it's a fun problem. I'm not sure.
Ooh, I think we see something new here on this next branching, though.
We do.
On the right branch, it actually forks, and on the left,
Goes the other way.
Had we seen that particular behavior before? I don't believe we have. Okay, but if we had something like 4 times 5, I guess the 20, the number 20, actually, we did have that behavior. So I think the right branch is probably a 20 as it's at its head, and on the left branch, that's a really simple, something like 4, but yeah, any prime times a prime.
But then but 4 times 20 would be...
It'd be too small.
Too small.
So the next one after 11, wow. Because each time we're increasing in the 2 factors on the coordinates. So, or at least one of them is increasing, but never decreasing. Let's say it that way. So if we start bumping up, I don't know, if 15 times 20 comes to mind, that's a huge jump. 14.
14 would work. Yeah, 14 times 20 sounds good to me.
Yeah, but
that is a big jump, but that would explain our circles.
Man.
Interesting.
Okay, ready?
Show us, Dr. Pickle. We're ready.
Okay.
10 times 20.
Oh no, it decreased.
Huh.
Oh, that was mean. That was mean.
This is a great illustration of how you can get misled if you have a hypothesis that's incorrect. So
that was a great hypothesis that I hadn't even seen. Like whenever you are constructing these mini universes, whenever you're kind of like God and you're constructing them, sometimes you miss, that would be a really interesting hypothesis. Because yeah, you're right. On the left-hand side, it goes 2, 2, 4, 4, 4, 5, 8, 8, 8, 8, 10, 11, and you don't expect it to go down to 10.
No.
It does, yeah. Yeah, so that was a really interesting hypothesis that seemed to be true.
It definitely did, because I mean, we had how many evidence? 12. We had 13 cases where it was holding true.
Right.
Well, and then on the 14th, all of a sudden, it's not true.
Yeah. Right. And that hypothesis still works for the top of the right branch each time. Those have increased every time.
Absolutely.
So is that legit, or is that just a pattern that happened to have worked so far? And this could be something crazy. Like this could be Dr. Pickle's favorite numbers in order that is based off of, or...
No, that would not be elegant. I would never do that. That would be criminal. To put you guys through that, my favorite, no, I will never do that.
But it could be numbers alphabetized in Latin or something.
No,
no,
please.
Okay.
It's beautiful mathematics. I'm a mathematician. I wouldn't do that to you guys. I promise. No, not alphabetized. It's not like the circle of the 0 has 1 hole and the 8 has 2 holes. No, it's nothing like that. It's beautiful mathematics. I put this sequence on the online integer sequence. What is it called? OEIS, the Online Encyclopedia of Integer Sequences. So it's on there. So it's not a weird kind of crazy sequence. It's a beautiful sequence.
Okay, I appreciate that reassurance.
Yeah. I sympathize, because I can say that comment probably came out of a lot of pain in your past of people doing horrible things like that.
Yes, indeed.
If we look at just the difference between the numbers and like proportionally, can we say that they are increasing more rapidly and then less rapidly? Like, is there any pattern that we can see? Because 2, 4, 8, 16, like that's our standard geometric sequence, but then we have 20 thrown in there before 32.
So you're thinking about the common differences?
Yeah.
2, 4, 8, 4, 12, 8, 24. Yeah, they're jumping up. Then 8, 16.
I just think, now that we have
40.
14 data points, we ought to be able to figure out what the next two are. If we just, if we kind of ignore the way they're broken down, if we just look at 2, 4, 8, 16, 20, 32, 40, 64, 72, 88, 128, 160, 176, 200, is that enough information for us to figure out what comes next?
I'm sure there's some rule that would narrow that down. Although figuring it out, it's not clear to me. Are the actual numbers that are being chosen, are they chosen independent of their factors?
Or do the factors control it?
Almost certainly they're not, because we have all these high powers of 2 in there. These are all even numbers. So
okay, so I can tell you it absolutely depends on the factors. Yeah.
Okay.
Yeah.
So
the factors. I could say more. I'll say more.
Just a little hint.
The shape.
Oh, this factoring shape? What? Growing tentacles all over the place, but they're getting bigger and smaller. And then, oh no, that I don't know if that helped. I assumed the shapes were getting more complicated because the numbers were getting bigger. But if the causation is kind of in the reverse somehow,
itself, so what if we have like circle turns to triangle? Never mind. I keep coming up with little ideas, and then when I say like, oh, that holds for these 3, and then I look at the next row, then it doesn't hold anymore.
Yeah. So my question is, do you think that we should leave kids with this? Or because I messed up earlier, maybe we should just, I don't know. What do you guys think? Should we just leave kids with question marks? I think this sequence keeps on going, by the way, so we don't have to end at 16. We can keep on going.
I think I really want the answer, but I don't want you to tell it to me quite yet. I want another hint and then see if I can figure it out. That's what I want.
Okay. So, how unique is there a smaller number that could go in here? In number 88, is there a smaller number that you could put in that?
And have the pattern work?
Yeah.
I mean,
so it would need to be.
Wait a minute.
So there's got to be a prime number on that side, and then.
So, is it possible that we have? Well, do I want to say it out loud or leave it to the kids then?
Would 24 work in that number? Because then never mind. You'd have 12 times 2, but we always
because you needed a perfect cube times
a prime number.
Yeah, but so 3 wouldn't work because then you got 6 times 4. So perfect cube times a prime number.
And it doesn't have to be a perfect cube. 12 would work down here as well.
Well, that's right. There are other. But if we have the smallest possible number that gives a new structure,
right.
That was a good hint. That was a good question to ask.
What about here? Let's say this one. Is there a smaller number that could make 20 in this up here?
All right.
12 would do the same one, right? Because you'd 4 times 3. Oh, but then it would be reversed because we'd have
correct. Then it looks like 8. 12 has got this pattern.
But 4 times 7.
8 pattern.
4 times 7, 28 would look the same.
But that's bigger than 20.
But that's bigger.
Yes.
Yeah. So
so now you're getting to what is unique about these numbers.
So we got the smallest number that has a pattern.
Is there any number that could go in here that would be smaller than 40?
So, thinking of three times
8, 24.
Okay, how would you split 24 as evenly as possible?
Oh, not by
according to your
4 times 6. Yeah.
Yeah.
So 4 times 6.
40
right.
is lost.
Yeah. So I'm liking this hypothesis that we're only that the prices that are showing up are only numbers that have one of these factor trees that have not yet, the patterns who haven't showed up yet.
Yes.
And it's the
That
smallest
you
possible.
have found it. So that is exactly correct. So just for you kids to reiterate what Math Dad just said, the pattern here is what's going to be the next one here? It's going to be the next pattern that you haven't seen yet. So we've seen a whole bunch of beautiful patterns here, but we haven't seen the one that's coming up. Can you find out what it would be? This is not easy because you have to look at, well, does 201 have a pattern that's different? Does 202, 203? Like you have to, it's not trivial to find out which is the pattern that comes up next. But that is going to be right here. Which number is the first number that gives a different pattern?
Different fractal pattern. And we're always choosing the factors that are closest to the average or closest to the center.
At each branch.
At each branch, you weigh them as evenly as you can. A number like 34, how do you split that one up? Well, 2 times 17. The 17 is really heavy, but that's as good as you can do. So that's how you split it up, 2 times 17.
And then it would look exactly like 4.
That's right.
Branch.
So you have
so we're not going to
34 is in the same family as 4.
And then we don't include it in our pattern because it's not a new one. And so every single number you get to, you just look, does it have a new pattern? So now that we know that, my real question is, can Math Dad predict the next number?
Oh.
Not easy, Math Dad.
No, not easy.
No, we want to save this one for the kids, of course. But I will point out, I do see
this goes on forever. This keeps on going. So if kids are interested, this obviously didn't work well with the chat not working. But if the kids want to, then they can email me later, and then we can have another session, not with you guys, but we could, we can figure out something that they keep on going with this sequence.
That's really cool.
Yeah.
But you are going to show us the last 2, right?
Oh, sure.
I'm expecting 256 to show up. There. Okay, yeah.
So there's
something in between.
There's something in between 200 and 256.
Right. So we're seeing lots of powers of 2 in these factors, and that had to do with the fact that we needed the first instance of certain factoring patterns to appear, and 2 is the smallest prime. So that explains that mystery.
That's why the 2 is in there so often.
Yeah.
But it's interesting that you also get, an 11 here, like out of the blue. Yeah. Oh, that's interesting. Yeah. And eventually all primes will be on there, will be represented somewhere in one of these factoring trees.
Right.
And we have not.
Oh, maybe not all primes. That's interesting. Yeah. I bet you all primes will, but it's not an obvious proof. You can definitely see that very high primes, you can't give a limit, because you could have on one side of the branch a power of 2, and then on the other side a single prime factor. And of course, that can get really, really big. But that doesn't mean that every prime number is in there. So that, I have to think. Interesting. A new puzzle.
Yeah. Well, this is a super fun pattern. I like it a lot.
Yeah.
Any guesses for that last remaining one on the board, Math Dad?
Well, we've had 16 on the right enough times that. All right, so maybe I don't want a multiple of 16. Maybe I don't know. Multiple
structure?
of 8 or 16.
There's the structure.
There's the structure.
Oh, so we've got a prime. So
what's 9 times? No, never mind.
Well.
So
200 and. Oh wait. Is that that's the 20 times 11.
I think it's.
I'm surprised we hadn't seen that one. Yeah, 20 times 11. Man.
20 times 11. Oh, okay. I was getting close. I was trying to figure out either 11 or 9 in that side one, and nice.
Yeah. there are multiple problems contained in this. But yeah, if
Yeah.
you're just given a bubble structure, can you find numbers that go in it? And then, yeah, can you actually predict where it would fall on this list?
Oh, super
Yeah.
fun.
Yeah, I love these kind of things. So I'd love to have you on again sometime whenever we've got chat, because that would just make it really sweet to be interacting with kids and
Yeah.
doing that. So
That's right. Well, what I've discovered is that I need the kids in the chat to bail me out on the hard
Yeah.
questions.
yeah, yeah, I know the feeling. Yeah, good. Well, thank you very much, you guys. That was totally awesome.
Oh, thank you.
Let me just, we might as well go to full screen for this last wave goodbye.
And I got to ask, did you
Yeah.
come up with this series?
Yeah. So this is my series. Up to this point, if you go to mathpickle.com, this is called integer fission, or integral fission. But I like the ice cream scoop idea. Like, it's totally wonky, but that's what I love to do, is to come up with interesting puzzles, and just to involve a wide range of kids. And I also like beauty. I'm very motivated by the beauty of mathematics, and so this is an example of a problem that I just find not just beautiful mathematically, but aesthetically very pleasing for kids to be working on this. And whenever kids work on this, I give them a blank slate without the numbers, but exactly what you see here, but with no numbers on it. So they get the correct order of things, and they know all of the rules. So they just have to figure out what number goes in each slot.
That's really cool.
Yeah, it's still a big task. Yeah.
Yeah, it's still complex.
Yeah.
Good. Well, you guys take care and be safe, and everybody out there, wash your hands and listen to your scientists and your mathematicians.
That's right.
Right.
Take care.
Yep.
We'll see you.
Bye.
Bye-bye.